All right. Okay, so we are starting the quiz 3 material. Well, we've already started. And we kind of started with the applying Newton's second law material. And since the number of views on YouTube is still not close to 240, I'm going to go over some of the things that were in that video, so that, because we really need that for the homework and for the problems we're going to be doing this week. Okay? So let's start off with an example. All right, so let's suppose I have a mass. It's m, like this. Okay, so let me start writing here. So a mass, capital M, is being pulled by a string, which I'll draw in a second. Okay, with tension, capital T, at an angle, theta, at an angle theta from horizontal. The question is, what is the normal force? Exerted by the frictionless horizontal surface. Okay, so let's draw all the forces that are involved. There's no friction. So I'm going to draw, so there's some tension T, but I'll draw the full three-body diagram here. I have a mass M. That's the mass. All right, somebody tell me one of the forces acting on this mass. Gravity, okay, right here, gravity. So it goes straight down. So that's Fg. And we already know the value of the gravitational force on the surface of the Earth. It's capital M times G. Yeah. Okay, yeah. What's another force? Tension. So we have this tension going like this. Okay? And so we're interested in what's happening to the mass and it's pulling in that direction. So remember, tension always pulls on both ends. Okay. Now, actually, while we're talking about tension, I remember a problem that I don't have the spring scale, but do you guys remember I had the little spring scale for it? Just a little side thing because I remembered it. Suppose I have a spring scale like this, just on the side here, okay? And suppose it's attached to a string that has some tension, okay? Let's say the tension of the string here is T, and the tension in the string here is T. If T is the force of the string tension, what will the scale register as a force? Will it register 0? Will it register T? Or will it register 2T? Anybody?
The scale is in the middle.
Yeah, so the scale is in the middle. And it's measuring the force being pulled. So if we know the tension on the two sides is T, will the scale measure T? Will it measure 0? Will it measure 2T?
0.
Okay, so I didn't do it with clicking, but how many people think it will measure 2T? Nobody. Okay, a few people. Okay. How many people think it will measure 0? How many people think it will measure T? All right, so 0 and T are kind of neck and neck. It will measure T. Okay? So think about a scale. Okay, so I don't have a scale. I mean, I suppose I could run in there and try to dig it out, but it might take a couple minutes to find it. But I have a little spring, okay? In order for it to measure a force, I have to pull, right? However, I can't just pull one side of the spring. I have to pull both sides of the spring with the same force, or else the spring is just going to accelerate in one direction and just fly out of my hands. So when I pull it, it's measuring the force I'm pulling on one side, but there's necessarily the same force on the other side. Okay? So I'm pulling with T this way, pulling with T that way, and the scale just measures. Now, the scale is not measuring the net force on the object, which is 0 because it's not moving. It's measuring how much I'm pulling on the two ends. Does that make sense to everybody? Okay. All right, so just remember that. That's sometimes a trick question that, that people are not familiar with. So when you have a measure of a force, you pull on and you have a scale, a spring scale like this. Oh, by the way, let me just write that. That's a spring scale. I'm not drawing it very well, but you have to pull on both ends with the same force, and that's the force that the spring scale reads. Okay, now back to this tension. All right, so this makes an angle of theta, and so, well, I'll do the complements later. And then what's another force that we have here? Normal force. Okay, so we have a normal force, Fn, that's pointing straight up like that. So let's take this to be the positive x direction, this to be the positive y direction. And now we're going to get the complements of t. Okay. The reason we're getting the x and y complements of t is if this block were to move, it would be moving in a horizontal direction. Does everybody agree with that? Okay. I mean, it could be lifted off the ground, but we're usually not asking those kinds of problems because that's a little bit weird. Okay, so we're going to get the x and y components. So we have t times, this is the adjacent side, so we have cosine of theta. And then we have t, this is the opposite side, so we have t times the sine of theta. Okay, so we're saying that this, it's being pulled along the ground, or the floor, or whatever. I guess it just said it was a surface. Okay, so there's no acceleration in the vertical direction. Oops, okay. Is that good, everybody? Now, I should mention, I didn't really say that in the problem that stays on the surface, but when you have a surface and you're saying and you're being told it's being pulled, you assume that it just stays on the surface. Otherwise, we'd say it jumps off the surface. Okay, so no acceleration in the vertical direction, so ay is equal to 0. Everybody's good with that? Okay. So, by the way, a lot of these problems are difficult simply because the first step of what you're supposed to do, other than maybe drawing the free body diagram, the first step might be complicated. You're supposed to, from this problem, figure out there's no acceleration in the vertical direction, ay is equal to 0. That's very often the next step you do after you draw the free body diagram. Okay. So now ay is equal to 0, then you use Newton's second law. Okay. Or if you want, you could call it Newton's first law because that's a special case where ay is equal to 0. So Newton's second law tells you that the net force y component is equal to the mass times the acceleration y component. Actually, let me write it with a capital M to match what I've written before. And so this is equal to 0. All right, so when you use Newton's second law, you write down the formula F net equals to ma, but then you also write down an expression for the net force. You say, now I'm going to sum up all the things in the net force. So I have the normal force, I have Fn. Okay, it goes in the positive direction. Right? And then I have this component here, it's going in the positive direction. Everybody's good on that? Because the arrow is pointing up. So I do positive t sine theta. And then I have this arrow going down, so I have a minus mg. Okay. And because this is the net force, and I say the net force is equal to 0, this thing is also equal to 0. Is everybody following me? So we draw the free body diagram. Decompose things into components. Next step, we say something about the acceleration. The acceleration is 0 in the y direction because it's not lifting off the surface. And then we use Newton's second law, the net force in the y direction is 0. And then we write down the sum of the forces that give me the net force, and that equals 0. So now I have an expression that Fn is equal to bringing these things to the other side, mg minus t times the sine of theta. Okay? Is everybody good on that? Does that make sense? Okay, well, let's go on. Let's do the next example. So we have two strings, and it's symmetrical. So let's say this is 30 degrees. It's 30 degrees. And then I have a vertical string. Then I have a 10 kilogram mass. And so let's say there's a tension T1 here, and there's another tension T1 here. The reason they have the same name is because they have the same tension. And the reason they have the same tension is because there's a symmetry to the problem that if I flip it over about this symmetry, there it looks the same. Is everybody good on that? When I say symmetry, this side, left side, is the same as the right side, so I know that T1 and both have T1, or both have the same tension, which I'll call T1. Now the other string is different though. So this one, let's say, has a tension T2. So remember, strings, they just pull on the ends inwards. So the question is, if this is hanging and it's not moving, the question is what is T1 and T2? Okay? Questions about this? All right. So which one seems to be an easier problem to solve for, T1 or T2? Okay, T2. Right. So it's easier because it only touches, well, it's the only thing touching the 10 kilogram mass. So if I focus on the 10 kilogram mass and draw its free body diagram, it seems like I can get T2 pretty easily. Okay? So here's the free body diagram for the 10 kilogram mass. We have T2 pulling up like this. And what's the other force involved? Gravity. Excellent. So we have Fg, which is the mass times the acceleration. So the gravitational acceleration constant, mg. Okay. And we might as well just write it out. So that's 10 kilograms is the mass times 9.8 meters per second squared. And that comes out to 98 newtons. Okay, since this mass is not accelerating, so we know AY for this mass. So this is positive y direction, positive x direction this way. AY is equal to 0. It's not moving, not accelerating in particular. Okay, and so we know that the net force in the y direction is from Newton's second law is the mass times the acceleration. And so this must be equal to 0. Okay, just like before. Is everybody following me? It's clicking. All right. What I don't want to do is to drive the car so fast that you're not following me. I try to go at a pace where you can kind of see where I'm going. Okay. So AY is equal to 0 because it's not accelerating. Therefore, from Newton's second law, the net force in the y direction is m times AY, which is also equal to 0. Okay, and now what we can do is we can say that the net force in the y direction is equal to, we have T2 pointing up, we have Ft going down, but we already said that's 98 newtons. And because this is the net force, we said net force equal to 0, this is equal to 0. And so T2 is equal to 98 newtons. Any questions about this? Now, what we can do is we can use that fact and solve for T1. So, in order to figure out T1, I have to focus on this point here. Now, this is a little confusing because this is just a bunch of strings tied together, and we're assuming, I didn't say it, but when we draw strings, we assume that the mass of the string is negligible. Okay? Otherwise, you would have to say the mass for length is a certain value, but we're not doing that in this course. That's much more complicated. Okay, so we have these massless strings, and so we have here this intersection. So think of this as a little dot with essentially 0 mass. Oops, thank you. Okay, And we have 30 degrees here, 30 degrees there. All right, so we're going to focus on this little dot. It's essentially a mass with 0 mass. Okay? Don't worry, it's not more complicated than if it had a mass. It'll turn out to be pretty straightforward. Okay, so we have tension T1 like this. We have tension T1 again like this. We have tension T2 going down. And we already know that the tension is 98 degrees. Okay. Now what we're going to do is we're going to do components. We do x and the y components. So we have here T1 times the cosine of 30. It's adjacent side to 30. Then we have here T1 sine of 30 degrees. And then we have this component here. And this will be T1 cosine of 30, but it's going in the negative direction. And then we have T1 sine of 30 degrees. Okay. Everybody's with me on that, components? Now, we're going to say that the net force, okay, because there's no acceleration, that means AX is equal to 0, AY is equal to 0, and that means that the net force in the x direction is equal to 0, and the net force in the y direction is equal to 0. Okay. Now, this is to answer your question. Okay? So, if we look at the x direction, are we going to actually solve for T1 by looking at the x direction? Not really, because I set it up. I said both tensions have the same value. So they're going to cancel each other out. I'll get an equation. T1 cosine 30 minus T1 cosine 30 is equal to 0. And then I won't be able to solve for T1 because I'll just get 0 equals 0. Now, sometimes people ask me, how did I know that I can skip that step? I'll just show you the way I figure it out. We say, okay, we'll do AX is equal to 0, therefore F net x is equal to 0, and then we'll write T1 cosine 30 degrees minus T1 cosine 30 degrees is equal to 0, and then we'll say 0 equals to 0, and we'll say, oh, that was a waste of time. And then I'll learn next time, I'm not going to do that, okay? That's the whole game. You figure out when you don't need to do this, and you learn, and you don't need to do it again next time. Okay? Because of the symmetry, you already took care of that. If you didn't know that these had the same tension, you would have figured it out at this stage, basically. At this stage, you would figure it out that the tensions in the two wires must be equal. But you already knew that. So now what we're going to do is we're going to say AY must be equal to 0 and actually get something useful. So then we get that the net force in the y direction is equal to 0. But then we can say the net force in the y direction, we have these components, T1 sine of 30. We have another T1 sine of 30. They're both positive. And then we have 98 newtons going down. So we have T1 sine of 30 plus T1 sine of 30. And then we have minus 98 newtons because it's going down. Okay. Any questions about this? Everybody's following along? All right. Now, this is equal to 0. Let's simplify this. So we will get that 2T1 sine of 30 is equal to 98 newtons. And then it turns out that T1 will be equal to sine of 30 actually ends up being 1/2. And so it becomes 98 newtons. Okay? So it turns out that both tensions are 98 newtons. But do not remember that as the solution to this problem. 30 was just a very special number where they ended up the same. If I said they were 45, then the number would be different. If I said any other angle, it would have been different from 98 at this stage. Okay? Any questions about that? Okay. Very good. So we'll continue on, but let's break it up and let's do this demo here. Okay, so this little demo is showing acceleration of this little cart. So almost frictionless, not quite, but almost frictionless. It keeps going a straight line pretty much with constant velocity. If I turn on a little fan, which way do you think the cart will accelerate? Well, yeah, I guess you maybe don't know which way the fan goes, so okay, it's blowing out this way. So which way do you think Okay, so let's figure it out. Does that make sense? Okay, so this is an example of Newton's third law. Remember, Newton's third law is for every action or if I press against this desk with a force of, let's say, 200 newtons in this direction, the desk is pushing me in the opposite direction with 200 newtons, exactly the same value. It's independent of the fact that the desk is not moving or the desk is moving. If A acts on B, the force of A on B is equal in magnitude to the force of B on A. It's always equal in magnitude but opposite direction. It doesn't matter about acceleration. Okay? So this force, there's a force that this fan is pushing the air this way. So if it pushes the air this way, the air is pushing because it's, you can think of it like a pushing magnet. The air is pushing the fan in the other direction. Does that make sense, everybody? Okay, now let's do a more complicated situation. I have here, oh, okay. That's okay. This way. All right, now let's suppose we have this fan here and a little foil, so something that prevents the air from passing straight through. What do you think will happen in this case? Some people say, go to the right, go to the left, stay still. Yeah, okay, let's just see what happens. All right. So the fan is being pushed in this direction because it's pushing the air, but then the air is pushing against this thing which is connected to the fan. So it's kind of like you're doing this, you kind of push yourself. You can't push yourself. All right. So in order to accelerate, you need to push off something else. Okay. All right. Now, we're going to start talking about pulleys. So everybody know what a pulley is? Pulley? Okay. So let me tell you. So pulley, didn't have this in my notes, but I realized I should talk about it. So pulley is just a little, sort of like a wheel. And we're going to assume that it's a massless wheel, frictionless wheel, and then you wrap a rope or string around it, okay? And then you can put masses on it, and you can let it. We used a pulley in some of the demos before, okay? But we're going to assume that the pulley does not have any mass for now, and that the string is massless as well. No mass. And the string has no mass. You could later do the case where the pulley has a mass, but that's a more complicated problem. Yeah. Yeah, no friction as well. I said it, but I didn't write it. No friction. Okay? So because there's no friction and this pulley is able to rotate, if you pull on one side of the pulley with a tension T, okay, sorry, if you pull, if this is you pulling on the string, okay, that's what I'm trying to mention. You pull on this, and then there's a mass here, then the string will pull up with the same tension. The pulley does is essentially reroutes the force. Instead of being in a straight line like a string would, it just makes it to a curve, a bend. Okay. Everybody following me on that? Okay, so what I'm saying is, if it was a straight string and you pulled on it with some force on the end of the string here, then it would pull on the, obviously it would pull on the mass with the teeth. But the pulley is just simply bending it around. Okay. Now, I'm going to show you a trick to solving some pulley problems that we developed. That after teaching this several times, I realized this was a shortcut. Okay, so I'm going to teach you a shortcut that's not in your textbook. And hopefully it's useful. If it's not, you can learn it the way it's in the textbook. Okay? Okay, so sometimes it's useful to define a curved path. as the positive direction, even though it's not straight. When doing problems with masses on pulleys, on a pulley. Let's say just one pulley. Okay. Okay, let me show you an example. Let's say we have a frictionless table. And we have a mass on the frictionless table. It's horizontal. It's very straightforward. Okay, let's say there's a mass M1. And let's say there's a pulley hanging off the end here. And there's a string that's attached to the mass, and it wraps around the pulley. And let's say there's a mass that's hanging off the pulley. Okay. And we can ask questions like, what's the acceleration of the system? The whole thing accelerates together. What is the tension in the string in terms of the masses? So it's a complicated problem, as you can see. This is why quiz 3 is a pain. Okay? Yeah, you can imagine just horrible problems like this. Okay? For example, suppose I made the frictionless table inclined. Now it's an inclined plane. Now suppose I add friction to the inclined plane while you have two pulley, the masses are attached by the pulley. Okay, so it can be very complicated. Now the trick here to make life simple. So I'm trying to make your life better, not worse. Okay, I'm going to define, instead of defining an x direction or y direction, I'm going to define an s direction. S standing for whatever you want, but I think mentally in terms of the word snake. Okay. So, because it's sort of like a snake that bends around a corner. Okay, so this is what I call the positive, this is what I'm going to call the positive S direction. Your book uses S for the uniform acceleration problem, so it's not unfamiliar to use that as a subscript. Okay, so this will be, it will be up over here, and then it will be to the left over here. All right? And it'll be useful in this direction. So this will be what I call the positive S direction. I just realized I just repeated what I wrote here, but okay, never mind. All right, so we're going to consider these two masses, M1, M2 as shown. Okay, so we want to know the acceleration of the masses and the tension of the string. Okay, what is the acceleration? They will move together. They'll both have the same acceleration. What is the acceleration of the masses, and what is the tension in the string? What is the string tension? Okay. Any questions about this? To solve this problem in the simplest possible way, you first consider, take a new sheet, we first consider both masses M1 and M2 together. All right. So let's take a look at the free body diagram for this system. So I have M1 over here. I have this thing. It's connected to M2 over here. All right. And now let's think about the forces. And remember, this is my positive S direction. This is the positive S direction. And let's consider the forces acting on the masses. Okay, so we're considering both as a unit, so we have to consider both of them. All right, sorry, I wrote this arrow right here that's going to get in the way of my normal force. So I have a normal force like this, but then I have the force of gravity, Fg, which is equal to m1 times g. Everybody's getting that? Okay. Now, because I'm considering m1 and m2 as together as a unit, the string is part of is internal to the unit, so I don't need to consider the string tension. Does that make sense to everybody? Like if I'm doing a free body diagram for me, I don't need to consider the tension, for example, of my muscle connected to my arm. That's part of me. Okay? It's like the string is part of the M1 plus M2 system, so that I don't need to consider the internal forces. Okay, but I do have to consider this weight of the of this mass, this Fg for number 2, which is M2 times G. Okay? Is everybody okay with this? Are we good? Now, if I'm considering this as the S direction, what contribution does Fn make to the positive S direction? Nothing, right? Because it's to the left is positive, it's perpendicular to this normal force. Everybody's with me on this? Okay? Fn makes no contribution. Fg, what contribution does it make? Nothing. Okay? So this is why it's kind of useful, this S direction thing. So the only force that's making a contribution to this positive S direction is this weight of this object that's hanging off. Okay? So we get that the net force in the S direction, so that the S is for this positive S direction, is, so should it be minus or positive? Sorry, minus or plus? Is it minus? Everybody see that? Because it's pointing in the negative S direction. This is positive S direction. Okay? So it'll be minus M2G. All right? You see how quickly we got that by using this S direction thing. Okay? And now we're going to use Newton's second law. And using Newton's second law, we have that the net force in the S direction, okay, using this curved direction, is going to be the mass of the whole system. So what will the mass be for this system? Will it be M1 or M2 or M1 plus M2? Yeah, everybody got that? We're considering M1 and M2 together at this stage. That's what we're starting with. So it's M1 plus M2. And then we have to get some acceleration, so let's call this AS, S for the S complement. Okay. Everybody is with me so far? Okay, so now we have two formulas for the net force. These things must be equal to each other. We have M1 plus M2 times AS is equal to minus M2G. And I have solved now for AS, it's just minus M2G divided by M1 plus M2. All right? That is the quickest way to get the acceleration of the system for these complicated pulley problems. You just simply use this S direction thing, consider both masses together. You get that the net force is just coming from this weight of the hanging object. F net is S is equal to minus M2G. And then F net S is equal to the sum of the masses times the acceleration AS. And then you set these two equal to each other, and you get AS is equal to minus M2G divided by M1 plus M2. Okay? Everybody good on that? So we got that pretty simply. Now, however, we didn't get the tension yet. In order to get the tension, what we're going to do is we're going to look at the simplest possible mass. So so we're going to consider M1 or an M2. M2 has the tension and gravity that's relevant. Okay, I'm going to be lazy. I'm going to look at M1 because M1, you have these forces, but they're not in the positive S direction, right? They're perpendicular. So there's going to only be the tension on M1. Is everybody understanding what I'm trying to do? I'm trying to get the answer in one step and be really lazy. If I now look at M1, so we're going to look at M1. The reason we're looking at M1 is because there's this normal force, but it's not in the positive S direction. So remember, this is the positive S direction. And we have the force of gravity, but this is not relevant because it's perpendicular to the positive S direction. And we only have this tension T here. Okay? Is everybody with me so far? So this is my positive S direction going to the left. The normal force is perpendicular to it. It has no component. Force of gravity is perpendicular to it. It makes no component. And so we simply have that the net force in the S direction is going to be minus t because it's in the negative s direction. Okay, it's going to the right rather than to the left. And then we use Newton's second law. And the Newton's second law tells me that the net force in the s direction must be equal to the mass, which is m1 in this case, times as. Okay. So now we have two formulas for the net force. So we have m1 is equal to, is as, let me just write it this way. I have m1, I'll just continue the way I was going to write it, is equal to negative t. So t is equal to negative m1 as, but we solve for as up here. We have a formula for as, so let's bring that in here. And so we have the minus signs cancel. I have m1 times m2 over m1 plus m2 times g. Any questions about this? So to review, what we did was we took this positive s direction thing, we considered both masses together, then these forces here cancel each other. We didn't have any components in the positive s direction, okay? And then we just have the force of the m2, the hanging mass, all right? And then we have the net force, we got as minus m2g. We said that's equal to, by Newton's second law, the sum of the masses times the acceleration. So we solved for the acceleration. And then once we knew the acceleration, we could get the tension by looking at one of the masses. It didn't really matter. I took m1 because it was simpler. And so I only have to consider this tension here because these forces are perpendicular to the s direction. So I have minus t. And then I have Newton's second law that the net force must be equal to m1 times as. Okay. And then I can solve for t. T is negative m1 times as, and plug in the value for as. Okay. Any questions about this? All right. Before I let you guys go, let's do a clicker question. Okay, let's say a 600-gram basketball and 150-gram baseball collide head-on. The magnitude of the force on the basketball is 7.9 newtons. What is the magnitude of the force on the baseball? Okay. All right, so the choices are 49.4 newtons, 31.6 newtons, 7.9 newtons, 1.26 newtons, E is 1.98 newtons. All right, so I'll open up the polling. All right. This problem shouldn't take too long, so go ahead and make your choice. All right, everybody made a choice? Okay, so I'm going to close it up in 5 seconds. Everybody clicked in? Okay, still moving, so everybody done? Okay. Let's see what people said. All right, a lot of people said C. All right. Okay, so this is Newton's third law. The force of A acting on B is equal to negative the force B acting on A. So if the baseball hits the basketball with a 7.9 newtons, then we have 7.9 newtons going the other way. Okay? That's all. That's all there is. All right, see you guys.